In this video, we talk about convolutional neural networks. So what is a convolution operation? Let's say we have two functions, f and g. We first flip one of the functions. Let's say g. Here instead of g of z, we have g of negative z. And then we shift the function by x. The integral means that we take the overlaps between the two functions f and g. When the functions are discrete, the integral becomes the sum. Now let's see how we can compute convolutions for images. So here let's say we have an image with a size of 3 by 3. And a convolutional kernel with a size of 2 by 2. So what we do is that we put the kernel on top of the input image and calculate the element-wise multiplications between elements and sum them all together. So if we do that, we have 0 times 0, which is 0. 1 times 1 equals 1. 3 times 2 equals 6. And 4 times 3 equals 12. So 12 plus 6 plus 1 gives us 19. We then shift the kernel to the right by one column and calculate the element-wise between the elements of the kernel and elements of the input image again. And what we have is 25. Then we move the kernel vertically down and we do the same thing. You get 37. And then we move it to the right by one column and calculate the multiplication again and sum together again, and we have 43. In a general case, if the input size is h by w, h is for height and w is for width, and if the convolutional kernel is also of the size of h by w, lowercase, then the output size is uppercase h minus lowercase h plus 1 by uppercase w minus lowercase w plus 1. Here we rewrite the formula for the output shift of the convolutional layer using nh and nw for the shift of the input image, and kh and kw for the shift of the convolutional kernel. Through multiple layers of convolutions, information available at the boundary of the images is reduced. If we want to keep the size of the output the same through multiple layers, we will need padding. In another scenario, if we want to reduce or increase the resolution, we will need stripes. So now let's look at a concrete example. Let's say we have an input image. and our kernel is 2 by 2. Without padding, our output size would be 2 by 2 as well. In order to avoid losing pixels at the boundary during convolution, what we do is that we add extra pixels around the boundary of the image. So here we add pixels of 0 around the image, so that the size of the input image is now 5 by 5. Taking the convolution between the input image and the kernel, we have the output. The size of the output is, so let's say we have 5 rows in the output image and 2 rows in the kernel. So we have 5 minus 2 plus 1, which is 4, which is the number of rows in the output. And doing the same thing for columns, we have 4 columns in the output. When we compute the convolution by putting the kernel on top of the input image and then move it to the right side until it reaches the boundary, the number of columns in which the kernel moves to the right or downward to the bottom is called the stride. Stride is usually equal to 1, but can be also different than 1. So in that case, we rewrite the formula for stride. For the height of the output is the height of the input minus the height of the kernel plus the padding, meaning the number of rows on both sides, which is ph, and plus the stride for the height sh, and divided by sh. We have a similar thing for the width. Now what if we have multiple channels on the input image? In this example, we have 2 channels. We also need 2 channels on the kernel. Then the convolution happens between the first channel of the input and the first channel of the kernel, right, which is here. And also between the second channel of the input and the second channel of the kernel, which is there. And then we sum the result together element wise, and eventually this is what we get. What if we also need multiple output channels? So we denote the number of inputs, Ci, I is for input, and the number of output channels, CO, and O is for outputs. And then we have a kernel of size Ci by kh by kw. This is the shape of the kernel, and more exactly 1 channel of the kernel. So up to here it is just like what you have seen in the previous slide. And now you have CO kernels like that concatenated together, so that in the output They are CO channels. The one-by-one convolutional layer is commonly used in convolutional neural networks. But what is its benefit? Actually, using one-by-one convolution, we would lose the ability to recognize patterns composed of adjacent elements. In this example, we have three channels. In the input image, and also we have three channels in the kernel, and we have two kernels like that. Now take the convolution between the kernel and the input image on all three channels. We take the value of this pixel times the value of this element in the kernel, the value of this pixel times the value of this kernel, of this element in the kernel, and again the time of this piece, the value of this pixel and the value of this element, and then we sum all the values, all the multiplication together. We get one single value, and we put here, and we repeat that for the whole image. We have one output channel. Notice that we have two kernels. So with the second kernel, we do the same thing, and we get the second channel in the output. So what we see is that the one-by-one convolutional layer is like the fully connected layer. The values of the elements in the input channels are very much like the input value at the input layer. And the value of the elements in the kernel are like the value of the weights. Now we talked about the maximum pooling and average pooling. Looking at the example, we have a 2x2 max pooling. We put the pooling window with a size of 2x2 on top of the input image. And take the maximum value, which is 4. So we have 4 for the first element in the output. And then do that again. We shift the window, the pooling window to the right, and then take the maximum, which is 5. That is the second element in the output. Take the max of the 4 elements. Here we get 7. And finally take the max of the 4 elements there. We get 8. How about average pooling? With average pooling, the difference is that we take the average instead of the max. We also have padding and stride. For pooling operations, with a pooling layer, we pool each input channel separately. So this is different from what we did with the convolutional layer. With a convolutional layer, we did that we added the inputs of each channel. If there are 3 channels in the input images and 3 channels in the kernel, the output has only 1 channel. However, in the case of the pooling layer, the number of output channels is the same as the number of input channels.